15 minutes for the presentation. Go ahead.
Thank you, Prof. Mays. My topic is observed and simulated summertime rainfall probability over West Africa. Over 70% of Africans earn their livelihood through agriculture. In fact, majority of the people in West Africa survive by subsistence agriculture. So this subsistence agriculture is predominantly dependent on nature. It is important that we study the nature, in particular the climate, because it affects directly the livelihoods of the people in West Africa. So one such important climate factor that we should study is precipitation, and most importantly, the variability in precipitation. So to do this, in this study, we tried to use observed data and simulated data. The aim was that we wanted to find out which hypothesis, which drivers, climate drivers are responsible for the rainfall variability that we observed in the observation data. And to do this, we used empirical orthogonal functions. So the empirical orthogonal functions, particularly what we call the PCA, principal component analysis, works like this. You have, for example, a two-dimensional data set. So suppose we have data that is already standardized, already normalized data. So the idea is that we want to find a new dimension that captures most of the variance in this data. So we can see that if we take this dimension, V1, it captures most of the variability, most of the variance in our data set. So the idea is that we remove this dimension, and when we do that, it's like we are protecting our data now in this direction. So also now we have to remove to again find another dimension that captures most of the variability in here. So the assumption here is that this P1 and P2 are both unit vectors. Now, these two unit vectors are orthogonal. So this can be written mathematically as, we can write this as, we want to find these such that we maximize variance. We maximize the variance in the projected data. So we are projecting this data on the P. So we want to find all those vectors that maximize the variance in our data set. 2. The idea is that whichever we get, we remove. So that means that our new data now will be x minus x v hat transpose. Now, this is the PCR way. It should be done repetitively until all the dimensions in our data set are extracted. Now, it can be shown, but I'm not going to show it here, that doing this is equivalent to Argmax of V of V transpose X V. Now we can see that this is already a constraint optimization problem, which can be solved using the method of Lagrange multipliers. So if we try to solve this using the method of Lagrange multipliers, we have that V transpose X V minus lambda into V transpose V minus 1, which is equal to 0. The constraint is this one. So if we try to differentiate this, we have that 2V transpose X minus lambda V transpose equal to 0. Now we try to simplify this to become V transpose X is equal to lambda V transpose. Taking the transpose on either side of this equation, we have that X transpose X V equals to lambda V, because this matrix here is symmetric. So what we have just shown here is that finding these vectors, or what we can call principal components, amounts to finding the eigenvectors corresponding to the biggest, the eigenvectors corresponding to the biggest eigenvalues in the data matrix X transpose X. Now, we actually want to show that these vectors here are orthogonal, because our method is empirical orthogonal functions. Now, we shall have shown that lambda, and there are two eigenvectors, eigenvalues. So meaning that using the definition, we have that X transpose X VI is equal to lambda I VI. So what we shall do is we shall multiply by Vj transpose on either side. So when we multiply here by Vj transpose VI. So what we are going to do is we shall look at this. This one looks like we have X transpose X Vj, but transpose Vi. But this is equal to lambda I Vj transpose Vi. So this one here is like lambda J Vj transpose Vi is equal to lambda I Vj transpose Vi. So what we are going to do now is to bring this on this side. So we have that lambda J minus lambda I into Vj transpose Vi is equal to 0. But the assumption is that lambda I is different from lambda J, meaning that this one are not equal to 0. So what can be 0 is this one. What this implies is that any two eigenvectors from the same matrix are orthogonal. So now we want to show that actually, if we remove one eigenvector from our data, all the other eigenvectors that we get using the PC algorithm are actually the eigenvectors of the data matrix X transpose X. So to do that, we shall use the definition. We have that X hat transpose X hat is equal to X minus X V hat transpose into X minus X transpose here V hat transpose. So the idea here is that we are going to say V is different from V hat. So if we multiply here by V, we also multiply here by V. So let us try to expand this out. We shall have X transpose X, then times the V, minus 2 X transpose X V hat transpose V plus V hat transpose V hat X transpose X V hat transpose V. Now we already showed that these eigenvectors are orthogonal. Any two eigenvectors of the same matrix, they are orthogonal. So that means that this is 0, this is 0, and this makes this 0 and this 0. So now what we remain with is X transpose XV. And now we can see that all the other eigenvectors of X transpose X are actually the same eigenvectors of X hat transpose X hat. Now, we have seen that this algorithm, we can get the principal components, but this would be quite hectic because we would have to do it over and over again. So now it would be better instead compute this data matrix and then we compute the agent vectors at a go. So what we did in my research, it was like I computed empirical orthogonal functions twice. I computed them for the temporal space and for the spatial space. So those for the temporal, I called them over the temporal, I called them EOFs. So those gave us the maps, and then these ones were giving us the time series. My results were like, from the results, I found out that 4 EOFs explained at least 50% of the variance in our data set, of the rainfall probability in our data sets. This means that there seem to be 4 processes that may be responsible for the rainfall probability over West Africa. I also found out that there is no simulated data that best mimics the observation. So all simulations in some way resembled the observation and in some way differ from the observation. So no best model. So what I learned from this was that for purposes of prediction, it is better that we use more than one models so that we can have all possibilities considered. We also discovered that there was a growing trend in the observation, and this seems to suggest that West Africa may be affected by the climate change. And therefore, we discovered that there was a cyclic pattern that was a cyclic pattern of extreme precipitation variation around the West Coast. So around the West Coast, there was extreme precipitation, and it was somehow cyclic. So what this means is that, yes, there is rainfall variability over West Africa, but if we can model and predict what is likely to happen in the next season, now that the extreme precipitation does not happen quite often, does not happen every year, so we can be able to predict what will happen and then be able to advise the farmers on which step to take. And in conclusion, we would suggest that we have been able to identify the patterns, but we have not been able to explain what is actually responsible for these patterns. So what we would want to do now is to understand what causes that variation in rainfall, what is responsible for those, and is it global, is it circulations? So we need to understand that, and that's what we suggest for future research. Thank you.
Yeah.
So, do you have any comment?
Not really. I think Dixon has done a good mathematical expression there. So I will leave the floor for the audience and the students.
Okay, good.
Okay, thank you. So I would like first of all to congratulate Andre, good job. And I will start by give some comment in the form, and then I will answer some. I will tackle some few questions. So let's just start from the abstract. So you have a business issue. So the abstract, you wrote in this paper. I think it should be in this cases. abstract should be the first, or should be in this case. And then somewhere you know the time series, there is a typos there. It's not the one. And then you have to merge also the abstract in one paragraph, not into paragraph. And also you have to improve your first chapter. So improve your first chapter. So just below the introduction, I think you should go there. 1.1 should be the motivation. And then after the motivation, you need to separate your first chapter into the subsection, like the section 1.2 should be the problem statement. So everything is there, but you will miss everything. So you have to separate. 1.3, you have to separate the measure or the main objective and the specific objective. So 1.2 should be the objective. 1.31, the major objective. 1.32 should be the specific objective. And we end by with section 1.4, the outline of the thesis. Okay, this will make your first chapter to be easy to read. Now, let me ask you the question. So, why did you choose to study the rainfall variability over West Africa instead of East Africa, for instance? Because I was interested in learning something new about a different region. I come from Uganda, and Uganda is in East Africa. So I looked at West Africa as something that would give me an opportunity to learn about the climate of West Africa. That's the reason. So because you came from Uganda, that's what the reason is that I wanted to learn now about West Africa, because I am from East Africa, so I didn't want to do. The overall idea is that there's rainfall variability everywhere, but for this essay, I decided to work on West Africa because West Africa is the other part of Africa that I would want to learn about. Is there any study, the same, did you find the same study in the literature about the East Africa, so that maybe you can compare it? Yes, I read about rainfall. A number of people have published about the rainfall variability in East Africa, but in this essay, I didn't report about the what was found out, because there was also similar studies done over West Africa. Okay, so let's go to page 7, your methodology. Section 4.1. So they mentioned that somewhere that there is a need for data to reduce the dimensionality of data. So what is the importance of reducing the dimensionality of data? Okay. The dimension, it is important to reduce the dimension of the data because it is hard to make meaning from something that is very, very large. So it is better you try to reduce and capture most of the information in the data, but you don't have to use all the value, all the data. It is important that we signal out the signal in the data so we can be able to make meaning, we can be able to learn from the data. So is your data in balance or no? It is. The data is a recording. They have just taken measurements. Now, to make meaning out of this data, you have to extract the signal. You have to extract something that is common. It's like you are trying to extract a pattern. So that's why it is important to reduce the dimension of the data. I see. So and then also, okay, talking about empirical orthogonal function. So what is the difference between empirical orthogonal function and principal component analysis. The empirical orthogonal functions are also referred to as principal component analysis. However, for the principal component analysis, we are just only interested in getting the vectors, the principal components. But for example, if you check in my results, there is where I'm plotting the graph, the map. So the EOFs are just another way of writing principal components, but now I used EOFs to refer to the one in space and also the one in like time series. So the best answer to your question maybe would be that following what I read, and it looks like principal component analysis is just a member of the empirical orthogonal functions. It's just a member of the family. Yeah, this was our looking for since okay, so let's go to page 8. So there you say something that since after the variance, since x bar is 0. Yes, how do you say it? You say since, so I didn't see somewhere where you put it 0. Because I did it on page 7. I standardized this that I normalized it by saying x is equal to x prime minus 1 x bar prime. So this process is standardizing, and when I do this, it means that I'm ensuring that the x bar is 0 for the data. But it was not mentioned before, because when you say since, it means that you say before that 0. Yeah. Then now there is some way that you mention about the KKT. Yes, what is it? KKT? KKT is an abbreviation of something. It is like a method that we use to set to solve the optimization problem. So these conditions, they are like used to come up with an optimization problem to set an optimization problem, and then we solve it. So in the presentation, I used Lagrange multipliers, but the general thing would be KKT conditions. So that's what I said there. So I would prefer that you should tell me that the KKT is an optimized condition to solve an optimization problem. Okay. So in which environment did you do your simulation? The simulations were not done by me. The simulations were done by the coupled model interconversion project 6. So this group of climate researchers, they simulated some data, and that's what I used. So that's what I considered as the simulated data. No, I mean, you got some plot, right? Yes. When did you do your simulation to plot? Oh, I used Python. Python, yeah. Which in Google Colabs or? No, I used Python. I used the Jupyter Notebook. Jupyter Notebook, yes. Okay. So did you use PyTorch or TensorFlow? No, I just used the Jupyter Notebook, just Python. Just Python. Yeah. So you wrote the code by yourself? Yeah, I wrote code. Then I also got some guidance from the internet, and I also got some guidance from my supervisor and also from my personal tutor, and then I came up with a code that I used to run all the models. Okay. So I'm going to page 11. So there, mentioned that all the R square value are less than 1. And so what does it mean in N4 variability? So basically, why I was doing this was because I wanted to see if the trend in my time series, if the trend is big or if it is small. So these R squared values being less than 1, it means that there is a mild trend. So that would mean that the rainfall variability is taking place and it is increasing, but it is increasing slowly. Yeah. Okay. So you mentioned something there since I'm from Cameroon. So I let you go. I want to know. Page 12, you said, for SEOF3 and SEOF4, the localized pattern in the model are more negative at the coast and area around yes. So that means that from this simulation, from this model, they show that around Cameroon coast, around the coast in Cameroon, there is a decline in rainfall, there is a decline in precipitation, in variability from the normal precipitation. So what can be the consequence of this in agriculture? So now that there is a decrease and we computed an anomaly, that would mean that the agriculturists around there, they are likely to be affected by drought that could maybe destroy their crops. So if I don't know, is Cameroon in West Africa? No, it is not in West Africa, but the region I considered was
the ones in West Africa. So it depends on like the one that is in Central Africa, it's not seriously the one that is not so there is a center. So there is other community like Gilabo, but Gilabo is also in East Africa community now. But it was also these things depending on yeah, yes,
so I think it's for me it's okay.
Yeah. So thank you. Give us 1 minute.